Hello everyone, my name is Van Hoàng Nguyen from the National University of Singapore. Today, I'll be presenting our research which improves fake news detections by better representing social context. We're living through a historical pandemic, and according to WHO, we're also fighting an infodemic of fake news. Fake news can even claim people's life with fake cures and treatment. In this work, we mainly focus on contextual fake news detections. Given a questionable piece of news, we can identify its source as well as how it is perceived by the social media. So if the source has a history of publishing false information and the news itself actually divide public opinion, not to mention that it is also denied by reputable media, it is highly likely that this piece of news is fake. This approach has the advantage of requiring no explicit evidence as well as making no assumptions of the information type, but it can be less explainable comparing to evidence-based fact-checking. When we take a step back, we realize that there is an online credibility ecosystem. If we check for the credibility of the news, then we have fake news detections. If we check for the credibility of source, then we have source factuality classifications. And if we check for the credibility of users, then we have troll bots detections. So the question here is how can we cross-leverage these different tasks but share the same online credibility ecosystem? The answer is later shown to be enhanced representations of the social context. This brings us to the contribution of this research. We propose a novel graph representations of the social context, including the social actors and their interactions. We also propose factual news graph, or fang, which is an inductive graph learning frameworks. fang can capture social structures and engagement patterns to improve representation quality. fang is also shown to be robust given limited training labels, as well as producing generalizable representation to related credibility assessment tasks. Although there are many choices for social context representations, we decided to choose a graphical representations because the social context is inherently a collection of highly associated social entities and interactions. And by applying the graph learning frameworks, we can learn a conditionally dependent representations, the network information exchange, and also model the underlying structure that is unique to the social context, such as user, communities, and news network. We can also formulate the problems as semi-supervised tasks, which is very robust in limited training label setting. In our social context graph, we have three major social entities: the users, news, and sources. We also model the interaction between them. So between users and users, we have the social friendship. Between users and news, we have the stance relationships, indicating the opinions the users have towards certain news. Between source and news, we have the publication relationship. In between source and source, we have the citation relationships, indicating if a source has cited another source in one of their published articles. We represent social entities by their textual features. More specific, we use a combination of TF-IDF vectors and weighted word embeddings. If the social entities are users, then we use their profile descriptions. The social entities are news, then we use the news content. And if they are articles, then we use their about us and homepage content. We also consider the importance of how a news is engaged on social media. That's why we want to capture the news user engagement patterns. Since this engagement patterns is actually temporal, we use recurrent neural networks as our aggregator, with user representation, timestamp, engagement stance as the inputs. The output of the RNN aggregator is then combined with the structural embeddings to obtain the news representations. Our model is inspired by Graph Sage, in which for each node, we first sample the neighbors, then we aggregate the feature information from the neighbors. The news representations can be optimized with an unsupervised context predictions or supervised node labels predictions. GraphSage has the advantage of being inductive, as well as it scales well with graph relations. Since the representation is both learned supervised and unsupervised, it has been shown to obtain good quality. We can also replace the vanilla aggregation with the temporal aggregation that is time sensitive. In our factual Muse graph, our proposed graph learning frameworks, the representations are jointly optimized on three objectives, which are proximity loss, stance loss, and fake news detection loss. We use a linear combinations of these three losses. In the first loss, the proximity loss, we divided the graph into two subgraphs of news source and users. Within each subgraph, we minimize distance between neighboring or positive nodes while maximize distance between remote or negative nodes. In the second loss, the stance loss, this is based on our intuitions that users sharing the common stance should have close representations. We first construct a projection functions from the representation space to the stance space. Then we add an auxiliary stance classification test with labels obtained from stance detector. Then the stance loss can be formulated as a supervised softmax loss with cross entropy. Finally, we have the fake news detection loss, which is fully supervised. We combine the representation of an article and its source obtained from graph stage. We then pass it through a fully connected layers. And then we have a cross entropy loss for our supervised objective. We conduct experiments to verify the effectiveness of our method. For the data, we use the Twitter dataset collected by the related works on rumor classifications and fake news detections. We also mine additional media sources, data, and our fake and real news labels are obtained from Snopes and PolitiFact. To verify the importance of contextual information, we compare our model against feature SVM. And for temporal importance, we compare our models against their time-ablated baseline, which are fang minus t and CSI minus t. And for the graphical importance, we compare GCN and fang against CSI. The metrics we're using to measure the fake news detection performance is the area under the curve or AUC score. So first of all, we can see that both 5 models outperforms feature SVM, indicating the importance of contextual informations. And then we can see that both fang and CSI outperforms their time-ablated baseline, indicating the importance of the temporal informations. And lastly, we can see that both fang and GCN outperform CSI, indicating the importance of the graphical informations. We're also interested in the model performance given the limited training data, so we plot the AOC score against the training percentage. And we observe that fang outperforms the baseline for all training portions. From 90% training data to 10% training data, GCN AOC drops by 16.22%, whereas fang AOC score only drops by 11.11%. So we have this fang minus S, which is the stance ablated baseline for fang, and we can see that the underperforming margin between fang minus S and fang increases as the training percentage decreases. This indicates the importance of stance classification auxiliary task. We also examine the representations produced by our models, so you can see that the homogeneity scores indicating the correlations between the representations, clustering, and the actual factuality labels is quite low for GCN, indicating that there are no correlations, whereas for fang, this homogeneity score is 0.051, indicating that the correlations exist. We also examine the media representations produced by both fang and GCN, and we can see that fang produced better representations. So for the media that has high factuality, we can see that they have their representations in the middle of the representation landscape, and they also have a very high intercitation density, whereas in GCN, the representation of both high and low factuality media, they're less differentiable. We also measure the representation quality on downstream source credibility classifications, and we observe that there's a 0.22 absolute F1 improvement compared with the textual features only baseline. So in conclusion, we have presented the advantage of our graphical representations of social context in fake news detections. We also demonstrated the benefits of stand detections and proximity modeling objective in our proposed framework. And we plan to do more experiment on more diverse user downstream tests such as troll classifications or bot detections. We also publicly release our source code and dataset here in this link. Let us end this presentation by a quote from George Bernard Shaw: "Beware of the false knowledge, it is more dangerous than ignorance." Thank you.